Right, so in this section, we are going to be talking about electromagnets. So 17.2 is titled Electromagnets. All right, so what is an electromagnet? So electromagnets are a magnet that are created by a wire carrying an electric current. So whereas in the last section we talked about permanent magnets, but there's another type of magnet, which are these kinds, electromagnets. So there's actually a relationship that exists between electricity and magnetism, and electromagnets prove that relationship between electricity and magnetism. The book talks about how this was actually discovered in 1819. Hans Christian Oersted, a Danish physicist and chemist, noticed that a current in a wire caused a compass needle to deflect. So when you brought it near there, when he brought the compass near this wire that was carrying electric currents, he actually noticed that the compass needle moved. So he discovered that moving electric charges create a magnetic field. And he actually made the discovery while he was in the process of teaching class at the University of Copenhagen. So you can see in the picture here on the slide, on the right-hand side there, I have a battery, I have wire, I have, looks like a nail in there, and you can see it's actually picking up that paper clip. And that's really all an electromagnet is. So I created a magnet with that nail just by sending electric current through it. And that's really all an electromagnet is. Now when you see the picture on the right, or the left-hand side there, sorry, when I see the picture on the left-hand side, they're showing you this thing that we call the right-hand rule in terms of electromagnets. If you curl your fingers in the direction of the current, your thumb will actually point in the direction of the North Pole. So it's called the right-hand rule. So you see there. So the poles are located at the end of the coil. So just like that nail, one side's going to be the North Pole, one side's going to be the South Pole, and you just use that right-hand rule to determine where the poles are at, so the North and the South. Now, if you think about, if I just told you, if you curl your fingers around the direction of the current, your thumb's going to point towards the North Pole. Now imagine switching the current. So if you switch the current, what's going to happen to your thumb? It's going to switch direction. So you can actually switch the poles of an electromagnet by reversing the direction of the current. This is an advantage over permanent magnets. As we saw before, permanent magnets, we can't do that. If you take a permanent magnet, you chop it in half, all you're going to do is do another north and another south. So the fact that you can change the direction of the current and change the poles is an advantage over permanent magnets. Application of electromagnets. Changing the current, as we just know, changing the current can change the strength of the electromagnet. So we just talked about how it can change north-south. But by increasing the current, I can actually increase the strength of the electromagnet. So more current, stronger electromagnet. So that's another advantage over permanent magnets. We can make them stronger and weaker to our liking, whatever we need them to be. So your book talks about a few applications of electromagnets. They talk about toasters. So the sliding switch on a toaster will actually turn the circuit on. It activates an electromagnet, then attracts a spring-loaded metal tray to the bottom of the toaster, making the toast essentially move up and down. So like the picture says there, a toaster tray is pulled down by an electromagnet while the bread is toasting. When the toast is done, the current gets cut off, and then the tray pops up. A travel application of electromagnets are these cool trains called maglev trains. And if you look at the name there, maglev trains, these are trains that are actually levitated by magnets. So you can see the cross picture on the top right there. We know if like charges repel, if I get a north-north or south-south, it's going to cause that train to actually be levitated off the track, and that's how maglev trains levitate themselves off the track. So they use electromagnets to lift a train a few inches above the track. It also reduces friction. So whereas in a traditional style train, you're going to get friction between the train and the track, you're not going to have this here. And then they actually use this same principle, so like repel, opposites attract, to push the train forward. So opposite poles attract and will actually pull the train forward, as you can see the picture on the right hand side there. And that video you guys are watching this week is actually one of these trains, Hyperloop trains. So instead of it being out like this, they actually have it inside. So now even imagine putting this inside of a tunnel, and now you're either further reducing friction with the air. Doorbells use electromagnets like they show you in the picture there. By you pushing the button on the doorbell, current is sent through electromagnet, which attracts a metal striker, causing the doorbell to go off. Scrap handling magnets like at junkyards, they will use the electromagnetism to track the metal when they want, move it to another area, turn the current off, and then you can drop the metal. Electromagnetic door locks, which I know a lot of schools have these, a lot of public buildings will have these. So in the case of a fire, that will actually shut the door itself so that you don't have to have someone there manually shutting the door. Right, so really all you need to build an electromagnet are these things. They are literally this simple. You need wire, some sort of a ferrous material like iron, and then a power source of some kind. So in the pictures a lot we use a battery. But that's it. It's all you need, and you're going to get an electromagnet. So what determines the force then that's going to be made inside that electromagnet is how much current do I have running through it. So let's say that if you look at the picture in the upper right hand side there, I have one 1.5 volt battery. If I add another one, so add two 1.5 volt batteries, that electromagnet is going to be twice as strong. If I add three 1.5 volt batteries, it's going to be 3 times as strong. So increase the current. How much iron or steel is in the core. So the more of that you have, the stronger the electromagnet is going to be. And finally, something we haven't talked about yet is how many turns are in the coil. So in the picture on the bottom here, they have 50, 100, 150, and 200. The more turns I put on that electromagnet, the stronger the electromagnet's going to be. The problem is, though, there's a problem with that. When I add more turns, what I'm actually also doing is increasing the resistance of the coil. So think about that, because you have to have the electric current going around and around and around and around, all of that. So what it actually does is it increases the resistance. And by doing that, think about what's going to happen. I'm increasing the heat there. So it can be slightly dangerous, obviously, to just continue to wrap and wrap and wrap around the coils there. So you got to make sure, if you want a really good electromagnet, it's going to have enough turns so that you have a great magnet, but not enough turns that I'm going to have the heat such so that I'm going to start a fire. So all of those things can increase my force in my electromagnet. How much current, the iron or steel that I put in the core, how much is there, and then how many turns are in the coil. But you want to be safe with all of these things, because just like other electricity, we can actually cause fires. Finally, the last thing the section talks about is, why do permanent magnets and electromagnets act in the same way? So they talk about similarities between permanent magnets and electromagnets. So on an atomic scale, electric currents create permanent magnets. So when you think about a permanent magnet that you have, so think about like a magnet that you have on your fridge, on an atomic scale, it's actually electric currents inside the atoms that are in that ferrous material, in that iron, or in that whatever permanent magnet is made out of, that is actually going to create the permanent magnet. And those, when I talk about atomic scale, think of like protons, think of electrons. So they actually behave like small loops of current, and these small loops of current mean that atoms themselves can actually act like tiny electromagnets with north and south poles. We don't usually see or notice the magnetism from atoms, because atoms are so tiny and usually the magnetism is too small to detect. The alignment to the north-south poles changes from one atom to the next. So on average, the atomic magnets will actually cancel out. It's when they're all lined up in a similar direction that we're going to get magnetic properties on a large scale. So permanent magnets have their atomic magnetic fields all lined up in the same direction, like you see in the middle there. So now magnetic materials on an atomic scale, their atoms will freely rotate and align their poles when a magnet is nearby. So freely rotate. Whereas if you look at the picture on the real top of this slide there, their magnetic materials or their atomic materials aren't going to freely rotate. So if you bring the permanent magnet near it, it's almost like they're stuck in concrete. They're stuck in stone. You're not going to move them. But the magnetic ones, imagine them almost like they're a compass needle. They're going to have that ability to move, and that's why you can get them to move on that atomic scale. So atoms and non-magnetic materials are not free to move, and that's why they're not going to be affected essentially by magnets. All right, so overall, electromagnets are really just magnets we create by running electric current in a wire around some sort of a ferrous material. Take iron, take other things. That is how we create electromagnets. So magnets created by electric current.